As the world of technology develops faster than ever, we're slowly running out of options when it comes to manipulating the macro and the microscopic world. But the possibilities are now here near ending. Welcome to the world of nanotechnology. It's a hidden world that deals with manipulating structures on the atomic scale and change everything from fields ranging from physics, medicine, chemistry, to materials. Since nano covers such a wide range, we'll explore one of its applications today. If we look at a lotus leaf, we'll find that water can't actually stay on it, which is often called superhydrophobicity. But why does it do this? Well, part of the reason it does this is actually due to the high surface tension of the water itself, which we can show using this experiment. The cup's filled with water, cardboard is placed on, but it seems like gravity doesn't affect it. This is partially due to pressure differences.
It is also due to the high attraction between the water molecules that these tiny forces of attraction actually play a factor in holding up the cardboard. These are the same forces that account for water's high surface tension and are what retains the droplet's shape. So if we look at water's surface tension here, we can see that it's quite a bit higher than all the other surface tension. Mercury's is also quite high, but that's why it's a liquid at room temperature.
So contact angles are formed when a liquid interacts with the solid surface. So if this black line represents the solid surface and the blue line represents the water droplet, then we can see here that this orange line represents the contact angle, theta. So you can have three scenarios. First, you can have a contact angle of 180, which creates a spherical droplet of water. This is similar to the lotus leaf. You can also have a contact angle of 0 degrees, which creates a long petal-like shape. And then you can also have a contact angle of 90 degrees. But most contact angles are between these three. So if we have a water droplet, the contact angles will give us three tensions. The first tension is between the solid and the liquid, the second one's between the solid and the vapor, and the third one's between the liquid and the vapor. This means that the intersection where all three meet is actually an equilibrium point, so we can actually represent this using a force diagram. Since each gamma represents a tension, each one actually pulls away from the intersection point, and because it's an equilibrium, the point isn't moving. So here's our three tensions. So we're drawing them pulling away from the point, and if we put in the theta goes right there. So because it's equilibrium, it's not moving. So we can actually write out a balanced equation and balance for the x components. So we take the solid vapor equals the liquid solid plus the liquid vapor cosine theta, and then if we solve for cosine theta, we get the solid vapor minus the liquid solid all over the liquid vapor. So if the surface energy for our solid vapor is greater than that of our liquid solid, you can see that we'll get a positive right-hand side, and therefore the cosine theta will be positive, which means that theta has to be less than 90 degrees because of the cast rule. Same thing happens if the solid vapor is less than liquid solid, we'll get a theta of over 90 degrees, also due to the cast rule this time. So if theta is less than 90 degrees, we'll get something like this. And if theta is greater than 90 degrees, so something with a high surface tension like mercury, we'll get beads of droplets. So now we know that we can predict how a liquid will behave on a certain solid once we know their surface energies. However, this equation only works on solids with perfectly smooth surfaces. Yet, we know that most surfaces in real life are rough, so we'll need to further expand this concept to include roughness. So roughness itself is actually defined as the actual contact area over the apparent surface area. So if this black line represents our actual contact area, then this orange line will represent our apparent surface area. And this will always be greater than 1 because of the peaks and valleys in the actual contact area. So if we look at a wetting example, this is where theta is less than 90 degrees, then this line represents what is perpendicular to the actual surface. So since it's wetting, our droplet has to be less than 90 degrees. So there's our droplet, and we'll shade that in. Okay, so you can see here that we actually have two angles. The first one is the observed angle, which is to the apparent surface area. So it's the blue line to the orange line. The next angle is the actual angle, which is the blue line to the black line. We can see that that angle is significantly bigger than the observed angle. So the actual microscopic angle to the black line, which is at a nanoscopic level, is actually much greater than the one that we measure. So the observed theta is actually much smaller than it actually is, which means that hydrophilic substances become more hydrophilic when the surface is roughened. So same deal here for the non-wetting example. There are 90-degree lines, and this time because it's hydrophobic, the angles are greater than 90 degrees. So our observed is still to the orange line, and the actual one is still to the black line. However, this time the actual angle is smaller than the observed angle. So we can see here that the observed angle is quite a bit bigger than the actual angle. So this basically just means that hydrophobic substances become even more hydrophobic when the surface is roughened. So basically the conclusion we get from all this is that roughening extenuates the pre-existing characteristics of the material. So like any technology, there's a good and a bad side. So the good side about nanotechnology is that there's so many fields you can apply it to. For example, in medicine, you can have nanoparticles that deliver chemo right to the cancer cells. In chem, we've all heard about nanotubes, in which they're used to strengthen. This is mostly because as surface area increases, you have more area to cause the reactions, so you get a lot more reactions and therefore many different characteristics. You also have energy, where you have a greater carrying capacity in a smaller area. Same idea for communications. And for materials, we can create incredibly strong coatings as well as super hydrophobic coatings, which we saw before. And even in consumer products, we could have contact lenses that never get dust in them or won't dry out. Unfortunately, there are some downsides to nanotechnology, including job cuts because of the inefficiency of nanotech. We can also have nanoparticles. We're not too sure what the effect of nanoparticles are because the technology is so new. And because nanotech is so hard to track, if nanotechnology did fall into the wrong hands, tracking Spyro would be very difficult. Because nano is a growing field, we can see that funding steadily increases every year. In fact, the US National Nanotech Initiative got $1.5 billion in funding last year. That's 5% of the $29.7 billion the US government gave to science last year. We can also see that worldwide, the US is still putting in the most amount of money for nano, but there are predictions that China could catch on within the next year. As for operating costs, because the tech is still so new, a lot of it is still being spent on research. In fact, 34% of it, or roughly $510 million. The main reason it's so expensive is because you need electron microscopes such as the SEM scanning electron microscope or the TEM, with high-end ones starting from around $250,000. For example, here's a mosquito eye from an SEM, so you can see how detailed the microscopes can scan, and obviously how expensive they'll need to be to do that. The future for nano is endless. It's basically like a periodic table has entered a new dimension, and each size creates a new characterization. We can have artificial eyes, where information is sent into tiny chips implanted in the eyes so that blind people could actually see. We have incredibly efficient filters because of the increased surface area, batteries with higher capacity because of a single layer of graphene, and we have gecko tape, which is based off the feet of geckos. So basically, if we take a gecko's foot and zoom in really close, we see tiny hair-like structures called setae. Each setae is then split into smaller places called spatulas. They're basically spatula-shaped places. Now these allow the gecko to stick onto anything it wants, including upside down. These little spatulas create actual intermolecular forces between the surface it adheres to, and these are the forces that attach the gecko, so that's really cool too. We can also have polymer solar panels, which decreases the area drastically, nanobots that can unclog clogged arteries, super hydrophobicity in de-icing or antimicrobial coatings, and we could even have anti-counterfeit inks. The possibilities are honestly endless.